we venture into simple ideas on area calculations and related stuff. The concept is very easy. We'll be perhaps able to summarize the ideas that we need to solve problems on area calculations in a few minutes. It's not going to take us very long. One, if I have the graph of a function y equal to fx, like this, say, between x equal to a to x equal to b. Suppose this is the graph of a function y equal to fx between x equal to a to x equal to b. And we want to calculate the area under this and the x-axis. So what we do is, essentially the entire area, if it's not a regular figure, is broken down into smaller strips. And then we carry out a summation based on the requisite limits. This is what we do. So here we select a strip of this kind. This is a strip selected, a sample strip. X, and this point is x plus dx. The width of this strip is dx. At x, I select a strip of width dx, and this is practically like a rectangle, and this ordinate is like y, which is f of x, which is like f of x. Then the area of the shaded region is going to be y into dx. Y into dx, where y is f of x. That's going to be the area of the shaded region. What we need to do is, we need to carry out a summation of all these strips starting from x equal to a to x equal to b. That's the area that we are seeking, the area under the curve, right, where y is written as fx dx, x equal to a to x equal to b, right? Sometimes the area could be entirely below the x-axis, right? We could have had a situation like this. Between x equal to a to x equal to b, this is the area, right? And our strips are these. At a given x, I select a strip of width or thickness dx. This is my y. Now realize y at this x is negative, right? So the area of the strip is y dx. That's going to be a negative number. That's going to be a negative number, right? But nevertheless, all these y dx's would be negative because the y's are negative, dx's are positive. So all the y dx's would be negative. Nevertheless, we sum it up starting from a to b, and at the end of it, we take a modulus, and that's going to be the area under the graph of this function, right? Now, part of it could be below the x-axis, part of it could be above the x-axis, right? We could have had a situation like this. Y equal to fx, and this could pretty much, between x equal to a to x equal to b, it crosses the x-axis at x equal to c. What we then do is, well, this area is negative, and these are my strips here. These are my strips here. This is my choice of strip here, and this is my choice of strip here, right? We deal with these two series of strips separately, right? This strip is like y into dx, right? Y into dx, and x runs from a to c. X runs from a to c. But we see that this is negative. So what we do is, around this we put a modulus sign, and I get this area below the x-axis. I get this area below the x-axis, right? And then we look at strips of these kinds. At a given x, this is my y. So y dx, integral y dx, x runs from c to b. X runs from c to b. That's the required area, right? Now, it might be misleading to believe that I'm going to select vertical strips all the time. There are occasions that it might be more efficient to select horizontal strips instead of selecting vertical strips. In this case, it's all right. Choice of vertical strips is simple, and it gives a direct calculation of the area. There are times, however, when we we, it might be superior selecting horizontal strips. For example, suppose I need this area. Suppose I need this area, right? What I do is, say between x equal to a, or say this is y equal to c and this is y equal to d. I need this area. Between y equal to c to y equal to d, I need this area. This is the graph of a function, right? What we can do is, again, this is y equal to c, this is y equal to d. My choice of strips in this case would be this. This is my choice of strip. This is my choice of strip. And so I'm selecting these strips, horizontal strips, each of thickness dy, say. This is dy. This is my x. This is a point P on the graph of the function x comma y. This is x and this is dy. What's the area of the chosen strip? X dy, isn't it? X dy. And then I carry out a summation. I integrate with y being my subject. X dy, y runs from c to d. Y runs from c to d will cover the entire area. That's the required area. Could I have even done it with horizontal strips? Vertical strips? I could have. You know, what I could have done is, with vertical strips, I could have computed this area. With vertical strips, I could have computed this area, for example, right? And then removed from the area of the rectangle this area. What is this area, for example? What is this area? I choose my strip this way, this. Okay. What would you designate as this strip at a given x? This is y equal to fx, fx minus c. Fx minus c is the length of the strip. Yes or no? Right? So fx minus c and into dx. Right? Dx is the width of the strip into dx. Where x runs from, say, a to b. Where x runs from a to b. Sum it up, x runs from a to b. That's going to be the area of this region, yes or no? Right? And all that I need to do is, this is a rectangle whose area I can readily compute, from which I can remove this. But which is better in this case? Choice of horizontal strips. So there are times when you would have to make a very superior choice. You can select vertical strips, you can select horizontal strips. So that will come out of practice, you know, what strip choice would be best in a given situation, right? Now, there can be two curves. So this is a curve. The y's of this are given by fxa, right? This is another curve. The y's of these curves, we'll call them y2, are given by, say, phi x, right? Yeah. And I need to calculate the area between the two curves lying between x equal to a to x equal to b. I need to compute this area. Right, between the two curves. What am I going to do? I'm going to select, say, for example, at a given x, a strip of this kind. This would be my choice of strip, right? This strip again is of width, dx. What is the length of the strip? y1 minus y2 is the length of the strip, of thickness dx. So the area enclosed by this strip is y1 minus y2 into dx. And I need to sum up all such strips starting from x equal to a all the way to x equal to b. So I need to carry out a summation of this kind from x equal to a to x equal to b. That's going to be the area of this dotted region. These are two curves that are not intersecting between a and b. But there could be two curves that might actually intersect between a and b. Say for example, this is say y1 equal to fx, right? This is y1 equal to fx. And say this curve is y2 equal to phi x. The y's of this are given by some function of x, call it phi x. And the two strips, the two curves intersect at x equal to c. And I want to calculate the area between the two curves starting from x equal to a to x equal to b. That means I want to compute this area plus this area. Yes or no? Right? What am I going to do? What would this strip be? This strip is going to be y1 minus y2 dx. Sorry, y2 minus y1, right? y2 minus y1 is this strip. This strip. Sum it up starting from x equal to a to x equal to c plus now this strip. This is y1 minus y2. That's y1 minus y2. y1 minus y2 dx starting from x equal to c all the way to x equal to b. That's the strip. That's the area. Right? Now, there could be a curve. So this is all in Cartesian. This is all in Cartesian. There could be a curve whose equation in polar format is known. R, distance of a point from the origin, theta, that the radius vector makes with the positive direction of the x-axis. That's a polar format. Different points represented by a r theta combination. Different points on the curve represented by a r theta combination. Say in the xy plane, this is a curve. The r of any point on the curve makes some angle theta. So this point P has polar coordinates. What are its polar coordinates? R comma theta are the polar coordinates of this point. R comma theta are the polar coordinates of this point. Right? Now what I want to do is for this curve, and I don't want to convert. So R is known as a function of theta this time. R is known as a function of theta. R could be say cos theta, R could be cos theta 1 into cos theta minus 1 and so on and so forth. Various things, right? R is some function of theta. Now what I want is between R equal to R1 to R equal to R2. I want this area. I want this area between R equal to R1, between two radial lines, R equal to R1 and R equal to R2. What do I do? Do you convert this into polar equation by saying R is root x square plus y squared x and y are the coordinates of this point and tan theta is y by x? Do you do that? No, that's ugly. Cumbersome. Right? You don't want to do that. You want to stick to, because then if you did that, then R1 and R2 and the theta 1 and theta 2 would have also to be converted into x1 y1 and x2 y2. Now that's not a situation you want. Right? I want this area between these two radial lines. The polar equation of the curve is given, R a function of theta. That's presented to you. Right? What does one do? what we do is we select a certain point P whose r is r and whose theta is theta, right? Hmm? Now, two very close r's, two very close points P and Q are selected on the curve. Two very close points P and Q are selected on the curve. If this is theta, let me say this is very small, call it d theta. Call it d theta, right? Now look at this sector. Almost like a circle because P and Q are very close to each other. Almost like a circle. What's the area of this sector? Half r squared d theta, isn't it? Half r squared d theta is the area of this shaded region, right? Half r squared d theta is the area of the shaded region. R is known as a function of theta, so you can plug in r as a function of theta, and then what you need is sum of all such sectors where r runs from r1 to r2. That's what you need. Yes or no? You need sum of all of this where r goes from r1 to r2, right? R runs from r1 to r2. That's the area. That's the area. This area. Why not? I need this area, right? What I do is I select an intermediate r. This is an intermediate r, and this makes an angle theta with the positive direction of the x-axis. Now I select a small angle d theta, as you see there in a separate figure, right? These P and Q are very close by points. This is almost like a circular region, arc of a circle with radius r. What's the area of this region? Half r squared into the angle it subtends. You know about that, right? Half r squared into the angle that it subtends at the center, half r squared d theta. Where obviously these angles are in radians, that's why, right? Half r squared. So half r squared d theta, and then what I need is sum of all such strips. Sum of all such strips is half r squared d theta summed up from r1 to r2, where r I can plug in as a function of theta. R I can plug in as a function of theta, whatever it is, and then obtain this integral with theta being my subject of integration, right? So if the equation is given in polar form for a curve, then this is what you do, right? Now, can I wipe it off? There are times you would need not the area of a curve, but you would need the length of a curve. Not the area of a curve, but the length of a curve between 2 points. Y is some function of x. I need the length of this curve between A and B. X runs from A to B. X runs from A to B. I need the length of this curve between x equal to A to x equal to B. This length I need. What am I going to do? How do I obtain the length of the curve? How does one obtain the length of the curve? Can you tell me? Area you know. I want to find, somebody gives you a parabola y squared equal to 4axa, and you want to find the length of the parabola, length of the arc of a parabola between x equal to 1 to x equal to 2, say for example, right? How do I obtain that? Anybody? Any suggestions? From all the calculus that you have ever learned. How does one obtain the length of a curve? Yes, please. No? Okay. This is how it goes. You select a certain point P on the curve. Alright? You select a certain point P on the curve whose x is x. Right? And now you take a, this is an accentuated view, but take a point Q very close to P. This is x plus dx, x plus dx. So, if x changes by a small amount dx, y will change by a very small amount dy. Yes or no? Right? Now this is, P and Q are very, very close points. Very close points. I join PQ. Do you realize this chord is practically the same as this arc? The chord PQ is practically the same as arc PQ. Arc PQ is what we seek, right? And what's a chord PQ from Pythagoras theorem? Root dx squared plus dy squared. Right? Yes or no? That's ds, which is not just PQ, but the arc PQ. ds is the same as the arc PQ. Because P and Q are very close, arc length and chord length are practically the same, right? That's what you get. And then you need to sum up all the DS's. You need to sum up all the DS's starting from x equal to a to x equal to b. Starting from x equal to a to x equal to b, that's going to give me the arc AB. Yes or no? Now the question is, hey, it doesn't seem like, you've dealt with something like this. Root dx square plus dy square. No, there is no rocket science here. This is x equal to a to x equal to b. You take a dx square common from this. If you took a dx square common from this, you have like a 1 plus dy dx whole square into dx. So now y would be known as a function of x. Say y equal to x square, for example. So if y is known as a function of x, you can find dy dx whole square. Dx integrate from x equal to a to x equal to b. That's going to give you the arc length. Yes or no? I mean, you could have had, say, y equal to x square is a parabola. Something like this. Y equal to x square is a parabola, something like this. Right? And between x equal to 1 to x equal to 2, you need the arc length AB. You need the arc length AB. Between x equal to 1 to x equal to 2, you need this arc. Clear? What are you going to do? You're directly going to say integral x equal to 1 to x equal to 2 root 1 plus dy dx. What is dy dx? 2x. 2x, right? So 1 plus 4x squared dx. This is a standard integral, root a square plus x square kind of a thing. Between x equal to 1 to x equal to 2, what is it going to give you? The arc length AB. It's going to give you the arc length AB. This is what happens. Does it make sense to all of you?